All right, well, in this video, we're going to be working through some of the stuff from Chapter 3, the one-way ANOVA chapter, and demonstrating how to do it in R. Now that we're finally getting into kind of the meat of the class, I wanted to demonstrate how I would deal with this really nasty data format that the textbook gives the data in. And actually, the way that I would deal with it is to really not use it at all. So what I would do for this data is, because it really is like, you can't just read this into R, and you could, but it would just be such a pain to try to actually get R to pull this out in a meaningful way. So how I would approach this is, I would, if I'm working on, let's say, problem number 10, and that's going to be what I'm going to be using for the example today, select this and then copy it over to a new Excel document, and then save this new Excel document as a CSV file. So I'd save it as a CSV file, call it whatever you want. I'd save it wherever I'm doing my analysis. In this case, I'm doing it in my R scripts file. And this is what I would use. Now, if you're in Excel, it's going to say, hey, if you use a CSV file, that's not a very advanced file format, so you're going to lose all your formatting. And it asks, do I want to keep using a CSV? And the answer is yes, because reading a CSV into R is really easy. So for me, I want to use a CSV, but you can use whatever you want. Anyway, this is the general strategy that I would use for the textbook data example, so that you don't have to deal with it. And then when I go to my data to read it in, I'm going to use my read CSV and assume I'm going to read it from that Excel book. And then I see that once that's read in, I see the top and bottom, and I do have 20 entries, which I should. And then I've got the row names, or the column names came in a little weird with the dots, because they had spaces and slashes and stuff in them in the original, but at least it read in appropriately. And again, that's just so much easier than trying to box with this kind of a data set. It's really kind of a pain. So I'd copy these out, put it in its own little data folder for the problems that you're doing, and then read those in separately, is how I personally would approach this. All right, so we're going to start with doing a by hand example. Now, I'm obviously going to have the code to demonstrate what we're doing, but I'd really recommend that you take the time and try to program this yourself. So I'm going to show you kind of give you the answer, but I'd really, really recommend taking the time when you're doing your by hand homework problem, and try to look at the formulas in the notes, and try to see if you could come up with doing this kind of a thing yourself. You can see it's not particularly super complicated, but yeah, see if you could give it a shot in doing it yourself. So first of all, I want to type in some general information. So I've got that I'm going to call on later. First of all, I've got I, which is we called A in our notes, and then J, which we called N in our notes, and again, there's multiple notations here. I is the number of groups. So I can just look in my data format. First of all, I see it's in a wide format, and that's just a good thing to know. And in this wide format, I see that I have 4 groups, so I equals 4. And so I'm just going to run that line. And then J equals 20. So what does that mean? Well, I have 20 replications within any individual group. Now, the other thing you can do here is look up the dimensions of your data. So it goes rows, columns. So I have 20 rows and 4 columns. So 20 observations within each of these groups. And that's where I'm getting my J equal to 20. Don't forget, your capital N is just the number of observations within each group times the number of groups. So that's my capital N. And again, that was A times little n. And now I'm going to actually start coming up with a few of the things. Now, you can use whatever variable names you want. I do YDD to stand for Y dot dot bar. And that is just adding up all of the different values. So the sum of dat, and if you just use sum on a whole matrix, it adds up all the numbers in the matrix, divided by the total number of numbers I added. So this is the grand mean. Now you could do like that's probably the best way to do a grand mean in R. Now, for the y1 dot bars, the yi dot bars, we have to do that for every I that we have. So we have 4 groups, so we need to find 4 group means. Now, how do I do that? Well, the group mean is just the mean of the first group, so I need to take the mean of the first column. So I literally use the mean command, and then I tell the matrix that I only want the first column, so I literally take the mean of the first column, and that's how my notation for the mean of the first column, or the mean of the first factor level, is y1 dot bar in my notes notation. So in R, I'm going to call the variable y1d for dot underscore bar, and then I'm just going to take the mean of that first column, which is the first factor level, in the wide format. And then I'm going to do that for the second column, the third column, the fourth column. And so now I have all of my y1 dot bars. Now I want to create a vector of all of the yi dot bars. So a vector where the first entry is the first column, the second entry is the the first entry is the mean of the first group, the second entry is the mean of the second group, the third entry is the mean of the third group, and so on. And so what I do is I just use that concatenate to combine all these results that I had earlier. Of course, if you have a different number of groups, you're going to be using a different number of these y blank dot bars. And again, hopefully you're giving this a shot and not just copying off of here, but really trying to understand what's going on and how you would get this just from reading the notes without ever seeing something like this. Because later on in a homework assignment, I'm not going to give you how I would do this, and I'll expect you to look at the equations in the notes and be able to write the R code from them. All right, so for the sum of squares treatment, well, again, how do I find this? Well, I look in my notes and I see, well, the sum of squares treatment is y I dot bar minus y dot dot bar quantity squared. So y I dot bar minus y dot dot bar quantity squared. Now, the trick that I'm doing here is you sum it up for each of the groups. But what I'm doing, the cool trick, is that if I use it as a vector, when I do the vector of y I dot bar minus y dot dot bar, it subtracts y dot dot bar from each one of these things automatically, so I don't have to do it. Otherwise, I'd have to do y1 dot bar minus y dot dot bar plus y2 dot bar minus y dot dot bar plus y3 dot bar minus y dot bar plus y4 dot bar minus y dot dot bar. And actually each of those quantities would have to be squared before I added them. But in this particular case, when I listed the yi dot bars as a vector of values, then I could just subtract y dot dot bar, and so it subtracted that grand mean from each of these group means all in one step. And then I'm going to square that difference all in one step. And then I'm going to add up all of those squared differences all in one step. And then I'm going to multiply it by n, like it said to in my notes. So I'm going to multiply it, or capital J in this case. So that's how I get my sum of squares treatment. My sum of squares total is just every single data point minus the grand mean, quantity squared, and add it all up. So that's how I'm getting my sum of squares treatment. And then the sum of squares error we mentioned in the notes, you can use kind of the shortcut where you just take the total minus the treatment, and then you don't have to actually do the error calculation, which frankly is the error calculation is kind of a pain. So for the degrees of freedom, this is just straight out of my notes, I minus 1, I times quantity j minus 1, and I times j minus 1 for degrees of freedom treatment, error, and total. And again, recall that I is A and J is N in the book's notation, but I tend to use I and J personally. And then the mean squared treatment is just sum of squares treatment divided by degrees of freedom treatment. The mean squared error is sum of squared error divided by degrees of freedom error. And then F is the ratio of mean squares treatment divided by mean squares error. So what I'm going to do is I'm going to use all this information. This is all of the components of my ANOVA table, the sums of squares, the degrees of freedom, the mean squares, and the F, and put this together. So how I do this is I make a data frame, and then I list each of the columns equals, and then I write out what I want it to equal. So the source is going to be, well, this is the text string indicating where the values are coming from. So the first row in my ANOVA table is going to be treatment, the second row is going to be error, and the third row is going to be total. And again, these look like they're all rows right now, but remember, these are all going to be columns eventually. So this is all going to be listed vertically when I print this out. The sums of squares, well, first is the total, second is the error, first is the treatment, second is the error, third is the total. Degrees of freedom, same order. Mean squares, treatment, error, and actually one of the things when I'm trying to make an ANOVA table is if I have a blank entry, I can't just leave it blank or ignore it. I actually have to tell R this is intentionally left blank or it's going to give me an error. So in the mean squares, I don't calculate the mean squares total. Normally that's left blank, so I just give R an NA to let it know that I'm intentionally leaving that blank. And then for the F statistic, I don't calculate F for the error or the total, so I have to put in 2 NAs. So when I run all of this and look at my ANOVA table, this actually looks like an ANOVA table that I would have seen except for those pesky NAs, but I have the treatment, the error, the total, the sums of squares, the mean squares, and then the F ratio, which is the mean squares divided by each other, and that looks pretty reasonable. Actually, later in this video, we'll double check this and we can go back and make sure that that looks correct. Oh, we'll do it now, I guess. So to do ANOVA in R using the built-in functions, so this was by hand, and again, I really hope you take the time to figure each of these out, not just try to copy what I do. And again, please don't do that because this changes pretty heavily depending on the situation you're in. So really try to make sure that you're understanding what's going on. Really try to build this yourself, straight from the equations in the notes, not just from this. And then maybe come back to this for help as opposed to just trying to copy and paste this for homework where you can really run into trouble real quick and lose a lot of points because you just copied and pasted without understanding. Now, note that the data set up here was given in a wide format. And actually, that's frankly kind of easier when we're doing it quote unquote by hand in R. But when we're actually doing it in R, we really want it in long format. So I'm going to make a new data frame called LDAT where I'm going to rearrange the data in long format. Now what I'm going to do is I'm going to take each of the columns and I'm going to put them in a row called out or in a column called outcome. And then in the first column, I'm going to call that my group. So I'm going to have a column called group. Recall we had like a column for the factor level 1, 2, 3, and actually that's what the group entries are going to be is 1, 2, 3, etc. And then the second column is going to be my outcome column, and it's going to show me what all my data are. So this is the data in group 1. And how do I know it's all in group 1? Well, everything in column 1 is from group 1 because column 1 is factor level 1. Everything in column 2 is from group 2 because column 2 is factor level 2. This is not a particularly efficient way to do it, but this is hopefully a way that's pretty straightforward and explains it to you. The C bind just says put this left and right to each other. So put group to the left of the data value. And then the R bind says stack on top of each other all these things. So actually, this is how it's going to look. We're going to have group to the left of outcome, and then we're going to have group 1 stuff on top of group 2 stuff, on top of group 3 stuff, on top of group 4 stuff. So let's run it and take a look at it. So if I look at my LDAT, then we can see I've got my group 1 stuff. There's 20 observations, 20 outcomes, all of group 1, and that's stacked on top of group 2 stuff. There's 20 observations there, all in group 2, and then that's stacked on top of group 3 stuff. And you can check if you want to. Sometimes I check to make sure that the first entry in group 1 and the first entry in group 2 and the first entry in group 3 are all different to make sure I didn't accidentally copy the same outcome column for multiple. So like let's say I accidentally put a 1 instead of a 2 there, which would have, that obviously would have been an error, but it's a really easy error to make. So checking on that. Now I believe that we talked in the t-test section about how important it is to use a factor command in R to make sure that R knows that these groups aren't numbers, that this isn't the number 1, 2, 3, 4, that these are actually groups. So I'm going to go on and tell R to treat this group variable as a factor instead of as a number. And then I'm going to run my analysis. The analysis is AOV, that's the analysis of variance command. The dependent variables on the left of the squiggle, and on the right of the squiggle is the group. And then my data is, again, this long dat. So when I look at this, I see the sums of squares, and actually I'm going to compare this to the ANOVA table we got earlier so that we can check in. The sums of squares for the group is 10.04. Hey, we got it right. The sums of squares for the error residuals is 196.03. Hey, we got that right too. And then the degrees of freedom also match. That's fantastic. That's great. You'll note that this format's a little weird. Actually, to get the better format, we use summary of the AOV command, but this gives the statistical tests, and recall that we don't do the statistical tests and stuff like that until we've looked at the assumptions. So I'm going to hold off on that until we go through how to check assumptions in R. But at least for now, we can see that our by hand work that we did earlier does seem to be lining up with the built-in function in R. And I'd highly recommend for your by hand work for homework problems. Again, not every homework problem is a by hand homework problem, but for the ones that are, that you check this out and that you make sure that your by hand work is matching up with the built-in function in R as far as the sums of squares and degrees of freedom and stuff. Because if it's not, either you ran the R command wrong or you did your by hand work wrong. So you have some double checking to do to figure out why there's a discrepancy. And I'd highly recommend you make sure you figure that out before you turn in your homework so you don't lose any points. All right, well, let's jump into checking assumptions in R, and then we can look at the nicer model summary once we're done with this. So first assumption we'll look at is independence. So again, this is from design. We're looking at the design and determining are there any data points that are connected to each other, thinking twins, brother and sister, things like that. Typically, this tends to be assumed, so we tend to not worry as much about this assumption. Now, if I know the run order, so let's say in this case, I know that this represents the run order of this particular data, then what I can do is I can plot the run order on the x-axis and then the outcome on the y-axis and look at a plot. And I want it to be pretty randomly looking. And in this particular case, this does appear to be pretty random, which is good. So yeah, my data appear to be pretty randomly distributed, and there doesn't appear to be any dependency on run order. But again, run order is only one source of potential violation of independence. It's not the only one. So looking at this plot doesn't mean that I'm good to go. Looking at this plot means that one out of literally an infinite number of problems isn't happening. So there's a whole ton of ways to violate independence. This means that run order isn't one that we're doing. Now, sometimes, run order is not an uncommon way to violate independence, so this isn't a bad thing to check if you know the run order. If you don't, you can't do this. But if you know the run order, this is a good thing to check, and actually it's a good tip to track the run order of each of your experimental units in your data collection when you're running your own analysis so that you can check this. That said, again, there's many ways to violate independence, and how you really check this as you go and look at the way in which the study was designed and see if there are any potential flaws in that design. So independence, especially in homework problems, we just kind of tend to assume, and that's okay. And if you have the run order, if you're given the run order in a homework problem, don't forget to run this plot. If you're not given the run order in a homework problem, then you don't run this plot. And you just kind of assume independence. For normality, I tend to write the residuals. So how we calculate the residuals is the resid command, resid of our AOV model. So I calculate that as E, which is our symbol for residuals. And then I use the QQ plot for testing normality. So I use the scale command inside the QQ plot, which just puts it on a standard scale. It doesn't actually change the graph at all. And then I add a line on there just so I can compare the dots to the line. In this case, you can see the dots are extraordinarily close to the line. This is probably the best fitting QQ plot I've ever seen. So that's a very good look. For the Shapiro test, I see that so this is a statistical test you can use. Again, I don't particularly I I do use these. I don't really look at them. I'll include them in a report, but if there's ever a disagreement between the test and the plot, I really just look at the plot. So the plot's where I make my decisions. The test is just an additional piece of support for any decision that I make. In this case, this Shapiro-Wilks has a very high p-value, and recall that in this particular case, we're testing for a significant problem. So recall that a low p-value is statistically significant, and that would indicate a statistically significant problem. A high value is not statistically significant, so we don't have a statistically significant problem. So make sure you walk through, if you're using these statistical tests for the assumptions, you really walk through the interpretation. But a high p-value is a good thing in a test of assumptions, a statistical test of assumptions. So the statistical test also indicates there's no issue. And again, that's not particularly surprising given that this is the best QQ plot ever. So for homogeneity of variance, the plot that I use is a box plot. I'm comparing these groups and looking at the size of the boxes and seeing, are the boxes, not are they located any differently, but are the sizes or the lengths of the boxes different. So this box is a little bit bigger than these two. So like 1 and 3 are a little bigger, and 2 and 4 are a little smaller. Honestly, these are all very close together. This doesn't appear to be an issue whatsoever. The other thing I know is that for this particular design, the number of data points in each of the groups is the same. We can actually check that using the table command, table, and then put in our data and the groups, and we can see that there's 20 observations within each group. So I know that this is a balanced design. I know this is pretty robust. Frankly, this wouldn't be a problem even if it were an unbalanced design, I don't think. But given that it's a balanced design, honestly, this isn't even worth a second glance. Now to test it using the Brown-Forsyth test, you can go to use the one-way tests package, the BF test. You actually have to re-give it the model for the BF test command. And we can see that the Brown-Forsyth test also shows that there isn't a statistically significant problem. So recall, in our tests of assumptions, we're looking at statistically significant problems, and we don't want significant problems. So this is not statistically significant, so we don't have a significant problem, which is a good thing. We don't want significant problems. So this agrees with our visual inspection. And again, I go with the visuals more than I go with the tests. So now we've passed all of our assumptions. We can actually look at the statistical tests. And after all that, it turns out that this wasn't statistically significant. So that's kind of a bummer. But we got the chance to run through the assumptions, and this is exactly how it'll go. Is you'll run through the assumptions, you'll check each of them, and then if they look okay, then you run the summary command on your ANOVA model, and you can look at the statistical significance and determine is there evidence to make a claim that any of the factor levels within the group are statistically significantly different than one another. And again, what you're looking at with the statistical significant difference is not, are the means in the sample different? Because of course they're different, at least slightly. The question is, in the population, do we have enough evidence that the means are different within the population? And in this case, we don't have enough evidence to say that. Now, recall that we have different interpretations for fixed and random effects. So for the fixed effects, I'm looking at these specific 4 groups and comparing them directly. For the random effects, what I'm saying, so with the fixed effects, I'm saying these 4 means are different, or these 4 means aren't necessarily different. With the random effects, I'm saying the factor levels have an impact, or the factor levels don't. The factor levels are different in this outcome, or the factor levels aren't. So in this case, there's not enough evidence to conclude that the factor levels differ in any way from one another, that the factor effects differ from one another, and actually that's also the same as the factor levels effects differ from 0. So in essence, depending on what your The way in which, recall that the only difference between fixed and random is the way in which you selected the levels of the factor. So depending on the way in which you set up your experiment to do that, you would look at this and make the appropriate conclusion. For fixed, you would say that these 4 factor levels don't differ. For random, you would say that there isn't enough evidence to confirm that any of the factor levels are different in the population of factor levels. Now recall, for random, we don't actually look at the box plots because I don't really care about these 4 groups. If it's random, these 4 were just drawn out of a hat. They don't really mean anything. What we look at is the variance components. So above, we already calculated the MSE. You can also do sigma of mod squared to calculate the MSE. But since we already calculated it, I suppose we'll use it. And then from my notes, the sigma square sub A is just the mean squared treatment minus mean squared error over capital J, or over N, depending on the notation. So I can calculate the intra-class correlation coefficient, and it's really small. That is, the percent of variation in the data that's due to the group differences is like 1%. It's a very, very, very small number. I can also calculate the confidence interval for the intra-class correlation coefficient, and these equations are long and yucky. But these are also good ones to practice typing in yourself before you just try to copy off the screen. And again, the goal is to get you some practice at turning equations from a paper into computer code, because that is something that you will be expected to do. So for now, I'm kind of showing you the quote-unquote right answer, but do try to give yourself some practice so that you can give it a shot on your own. All right, so in this case, I see the lower limit is negative, and again, we talked about how that's kind of awkward because you can't have a negative percentage, so that's kind of silly. And then the upper limit is positive, and then of course the observed intra-class correlation coefficient, so a very low positive number. All right, well, we'll close out this R session by doing some post hoc testing and then talking about power analysis. But for the post hoc testing, let's change the example a little bit. So the example I'm going to use is a variety of different tensions and how it affects breaks in yarn. So I'm going to run my model, and then I'm going to check my assumptions. And again, this is the first step with any model you run. Now this is, I mean, the last one was just all the data were perfectly on the line. This isn't that, but this looks very, very good. So this is not a problem at all here on the normality. And again, some students get worried because of these little variations. We're really looking for big patterns of problems, not these little variations. So this looks very good. Checking the box plot, there does appear to be, well, no, this is still fine. I guess I don't even think I've done this. So let's look at the table of warp breaks broken down by the different tensions and make sure it's a balanced design. It does look like the independent variable has an equal number of observations within each level of the independent variable, so it is a balanced design, which means I'm not worried about this at all. Even in an unbalanced design, this is probably fine, but given that this is a balanced design, this is fantastic. So we don't have to worry about anything here. So this passes all of our assumptions. Maybe not this one with flying colors, but it's just fine. So now we get to look at the results of the ANOVA, and we see that there's a statistically significant effect between the different tensions. So that is, here it looks like I get more breaks on low tension than I do on high tension, but I wasn't sure if that was just for my sample or if that was for the population. It looks like this ANOVA suggests that I would expect to see that in the population. I don't really know, is medium lower than low? Is medium higher than high? I don't know where medium fits in with these groups, so that's something I'll look forward to finding out in my tests. And my ANOVA doesn't tell me that. It just tells me that at least one of these groups is different from at least another one of them. So now I run my post hoc tests. So the LSD, we can use pairwise t-tests, and the LSD is using the p-adjustment method of none, and that uses no adjustments. What it gives me is a matrix of p-values. So this would indicate that the p-value comparing the low tension to the medium tension is 0.01, so below 0.05. The p-value comparing the low tension to the high tension is 0.0005, so well below 0.05, and the p-value comparing the medium to the high tension is 0.238. So what this would say is that low is different than medium, medium is different than, low is different than medium, low is different than high, but medium is not statistically significantly different than high. So that's what this would say. Now we can use a better p-adjustment method, because remember LSD doesn't do any adjustment, and we can see that by p-adjust method equals none, but we could use the Bonferroni method instead. Now this is tricky, and you have to be really careful of this depending on the software. Sometimes the Bonferroni method just kind of gives you a different alpha to compare to. But in software, if you ever tell software that you're using Bonferroni, what you'll notice is that sometimes what the software will do is actually multiply the p-values by that k value so that you still compare to 0.05. So this is where it's important to understand what your software does. In this case, because my software R, instead of me mentally doing the arithmetic of changing the alpha value, when I tell it I'm using a Bonferroni, it does the arithmetic for me so that I can compare to the regular alpha value. So in this case, I'd compare all of these to 0.05. And again, the reason I know that is because I'm familiar with my software and how it does a Bonferroni correction. In any case, recall that both of these probably aren't the appropriate correction for pairwise comparisons. The real correction I want to use is Tukey's HSD, which is the Tukey's HSD command. This does each of the pairwise comparisons. It gives me the size of the difference, the upper and lower end of a confidence interval, and then the p-value that's been correctly adjusted. So this is the p-value that I would use if I were doing this for a real client or on a real consultation or job. So I'd compare medium to low, and I see that there's a statistically significant difference between the groups. High to low, there's also a statistically significant difference between the groups. And high to medium, there doesn't appear to be a statistically significant difference between the groups. So the only pairwise comparison that we don't have enough evidence to claim is different at the population level, or enough evidence to support that it may be different at the population level, is the difference between medium and high. Note also that here, just because I say that they're statistically significantly different doesn't mean that that has a practical impact. So it doesn't mean that they're practically different. Now we talked about Chaffee's test. If I were doing a whole bunch of contrast, this is what I would do. Chaffee's test is a really, I'd never use it for the just pairwise comparisons. I'd use my Tukey's test that we were doing above. But this is how you'd run it using the Desk Tools package. With a capital D and a capital T if you have to go install that. And then Chaffee's test, capital S, capital T, and it can be really annoying if you forget the capitals. Not that I have experience with that at all. But then you look at this and you can actually see the p-values, and you're getting similar conclusions to what we saw with Tukey's, though the p-values are all slightly bigger than what we saw with Tukey's because the Chaffee's test is less powerful. Or yes, less powerful, more conservative. All right, the final one is the Dunnett's test. So for Dunnett's test, we needed a control group, so I'm using a completely different example. We've got the control and then a couple of different diseases, and we're looking at the efficiency of lung dust removal between control and diseases. I think this is kind of a built-in example. So I'm just going to create some groups that are these different conditions, and then run the analysis where I'm comparing control to the different diseases. So this is, again, from Desk Tools. We can implement the Dunnett test, capital D, capital T, and we give it the outcome and the grouping variable, and it gives us back the comparisons. Now note that disease 1 isn't compared to disease 2, and the reason is because in Dunnett's we only compare everything to the control. So in this particular case, we see no statistically significant differences from the control. All right, well, the final thing we're going to do in this video is talk about power analysis. So power analysis in R, I'd use the PWR package. The command is pwr.anova.test. Now you need to give it, for power analysis, you can give it any one of a combination of things and you leave out one. So the things are the effect size F, the number of groups, that's not one you can leave out. But power you can leave out and significance level you can leave out. And then the other one that isn't listed here because I want it to solve for that is the sample size. So you leave out the one you want it to solve for and it solves for it. And so where am I getting these values? Well, the significance level alpha is my typical significance level. Power 0.8, 1 minus beta is my typical power level that I use. Sometimes if you want a really high powered study, you'll do 0.95, but very, very often people use 0.8. K is just the number of factor levels I'm planning on having. And then F represents the effect size. Now, what is F? How do I get that? Well, if I were actually doing this, I would have run a pilot of the experiment that I'm doing the power analysis for to determine the sample size for the whole experiment, and I would have run a pilot study. And in that pilot study, I would have calculated an F statistic. Well, what is this F? Well, it's not the F statistic we calculated above. This is a measure of effect size. Well, how do I calculate that? Well, golly, I don't know. For me, I went and Googled it. I Googled how do I calculate effect size F in R, and I got a list, and it told me how to do it, and it gave me a package, and it showed me how I could calculate it by hand. And so with my data from my pilot, I utilized that package, or I calculated it by hand, and it wasn't necessarily an easy calculation. But by using pilot data, I was able to get this effect size F to give me a good idea of what the size of that effect would be. So given all of this information, again, these ones are easy because you just kind of assume them. This one's pretty easy because it's the levels of the factor you're interested in. This one can be pretty difficult. You should be finding it from previous literature or doing a pilot study. I will admit that many people just use prefabbed, made-up rules of thumb when they're doing this, but really the best practice is to use a pilot study to get an estimate for that. And it's not particularly difficult. Just run your experiment with a couple of trials and see what effect size you get out. In any case, when you run this in R, you'll note that it repeats all of the things, and then the one that you didn't put in my case, the sample size, it spits out a number for. So in this case, to get this particular effect size, to only have a type 1 error rate of 0.05, to detect this effect size 80% of the time, I'd need a sample of 36. You always round this up. Even if it's a low decimal, you round it up. I'd need a sample of 36, and it makes a note. 36 isn't the total sample size in the 4 groups. 36 is the number in each group. So I'd need 36 times 4, total sample across all the groups, 144 experimental units. And this is good to know because the difference between collecting 36 experimental units and 144 experimental units is pretty darn different, especially if you're paying people or something like that, or your materials are expensive in either money or time. So this is important to be able to be aware of and to be able to account for. So in this case, I'm going to need 144 individuals. And note that even with all those individuals and this particular effect size, I'm only going to detect that effect size 80% of the time. So if it's there, if it really does have this effect, I'm only going to find it 80% of the time. So that's a reason that you may bump up the power. Now, why would you not bump up the power? Well, let's bump up the power to 0.95. That way I'll detect that effect size 95% of the time. Let's see what happens. Well, my sample size went from 36 to 56. So now instead of needing 144 total, I need 224 total, almost 100 more people to get this effect size to have a higher power. So this is the reason that people tend to not have bump up the power in their studies, is because it tends to require a larger sample size, sometimes a much larger sample size, depending on the context. So this has been a discussion of how to implement ANOVA in R, including how to do some of it by hand, how to check the assumptions, how to calculate variance components for understanding the results of a random effects ANOVA, how to do some post hoc testing, and how to do a power analysis for ANOVA.